Hello, my name is Hantran. In this video, we're going to be defining some Python functions that allows us to calculate for bubble pressure, bubble temperature, dew pressure, and dew temperature. And then we'll be using all those functions to generate some plots for a binary vapor liquid equilibrium phase diagram at a constant temperature and a constant pressure. So we are actually given a problem, and the problem tells us that we have a binary mixture of benzene and toluene. And it also tells us that the constant temperature is going to be 393 Kelvin and the constant pressure is going to be 150 kilopascals. And so in a previous video, we ran through Raoult's law, which is the liquid mole fraction of a component times the saturated vapor pressure equals the vapor mole fraction of component times the total pressure, and that equals the partial pressure. And so we ran through that equation and how it was used for mixtures, and then we talked about the bubble point and how the two cases of bubble pressure and bubble temperature, and we derived the equations for that. And then we also talked about dew point and the two cases of dew pressure and dew temperature and derived the equations for that. So now we're going to be using those equations, and if more detail is needed on how we got to those equations, please go back and look at the previous video that has how we got to these final derived equations. But we have these equations, so we're going to use them to write the Python function. So before we go into writing the functions, let's head on over to Python and import some toolpacks that we'll be needing. And so the first thing we need is this wonderful repository, and this repository allows us to use some tools to calculate the saturated vapor pressure, which we'll be needing. So there's these toolpack and che.py. This allows us to calculate for the saturated vapor pressure. And then there's also different properties in this toolpack. So if we go to data, there's the benzene that we'll be using and the toluene that we'll be using. So this has everything that we need, and so we actually grabbed the raw data for the raw code for the che.py pack. And so to get that raw code and information into our code, we're going to copy the URL, and in our code we're going to write !wget. So this is going to get the information from a URL, so -n -q. We're going to just copy and paste the URL straight in and shift enter, and now that all of that wonderful information that was in that repository is now available to our use in the code. So now some other packs we'll be importing. We will be importing NumPy. So NumPy has many different mathematical and more mathematical functions other than just multiplication and division. There's the summation, which we will be using, and so we're going to import NumPy. We will also be importing che. That's the wonderful repository that we just imported, so we will import that as che, and then we will also from scipy.optimize, we will import root. So this root function allows us to solve for those nonlinear equations for dew temperature and bubble temperature, and so we'll be using that in our functions. And then from plotly.subplots, we are going to import make_subplots. So this wonderful thing allows us to plot the phase diagrams that we'll be doing later. So we're going to shift enter. Now we have those wonderful tools that we can use, and so yeah, let's get right into writing our functions. So the first function we're going to write is the bubble pressure. So if we look in our notes in the equation that we derived in a previous video, the bubble pressure is the summation of the liquid mole fraction times the saturated vapor pressure from the first component for all the components. In our case, we only have two components. So before we before we begin writing our functions, we need to import the different components we'll be using. So we're going to name that as P, and we are going to be using that toolpack that had the data for benzene and toluene. So we want the benzene and toluene properties. So we're going to use che.props props, and we want to list out in an array the different components we'll be using. So if you were using more components, you would list them all out here. We're only using benzene and toluene. So the first one is benzene, and then the second one is toluene. Okay. Now we have the components we're using. Now we can begin writing the bubble pressure. So we're going to define a function. We will call it bubble P for bubble pressure, and that needs the liquid mole fraction and the temperature in order to calculate the saturated vapor pressure. So we'll be using X and T for those as those variables, and we wanted to return, so we're going to use np.sum. This is the summation, and we wanted to sum the mole fraction, the liquid mole fraction, times, so in order to get the saturated vapor pressure for each of the components for benzene and toluene, we're going to be using that P that we named earlier, and this P here, P dot, and in the tool pack, PVAP, PVAP is what is used to calculate the saturated vapor pressure. So we'll be doing PVAP and at a certain temperature, which is what is needed to calculate saturated vapor pressure. And we'll shift enter, and that is our function for bubble pressure. So now we're going to move on and do bubble temperature. So bubble temperature is a little more tricky because it is actually a nonlinear equation that needs to be solved, and so we'll be using kind of like a nested function. So we'll be writing a function within another function. And so in order to solve this, we are going to be using the root solver, and so the root solver solves an equation that's set equal to 0, and it requires an equation as well as an initial guess, and it is all done within arrays. And so we are going to define the bubble T, and that will be for our bubble temperature. And again, we need the liquid mole fraction, but now we need the pressure, because the equation for the bubble temperature is the pressure minus the bubble pressure equals 0. And so we will need the pressure. And so now is our nested function, so we're going to define an equation, and this equation is going to be an array, and so we're going to have a vector here, and then now we need to break down what is in the vector. So in the vector there's going to be a temperature, and that will be the first index of the vector, and we want it to return the equation that is the pressure minus the bubble pressure. And so again, it is done all in arrays, so we need to put it in square brackets. And so we have the pressure minus, good thing we already defined our bubble pressure, so we don't have to write out the NP sum. We just put in the bubble pressure, and that is for a certain mole fraction and a certain temperature. And then now we want to return the root function, and so the root function again is what's going to solve the equation. So we need to put the equation or the function that has the equation that's trying to be solved. So we name that as EQU, and then we need an initial guess. So we can just guess 298 kelvins. That can be our initial guess, and we can shift enter. And that is our bubble temperature, all nice and defined, the function. And so now we're going to move on to the do pressure. And so we're going to define a function called do P. And if we look, the do pressure is 1 over the sum of the vapor mole fraction divided by the saturated vapor pressure. And so now instead of the liquid mole fraction, we need the vapor mole fraction. So that we'll just call Y, and we need again the temperature. And so we wanted to return 1 divided by the summation. So we're going to again use np.sum, and it is the sum of the vapor mole fraction divided by the saturated vapor pressure. So we have the vapor mole fraction divided by, again, we're going to use those CHE tools, and so that's going to be P dot P VAP, VAP, of that certain temperature. And that is our due pressure defined. And so now we need to define our due temperature. So again, similar to the bubble temperature, the due temperature is an equation that needs to be solved to actually obtain the due temperature. So the due temperature is set equal to 0, and it is 1 over the summation of the vapor mole fraction divided by the saturated vapor pressure minus the pressure. And so this is very similar to bubble temperature. It's just instead of using the bubble pressure, we'll be using the due pressure. And so we're going to define, it's going to again be kind of that nested function within a function, because we're going to be returning the equation and then using that equation in a root, which will be then returned. And so we're going to define this as due T, and we will be needing the vapor mole fraction and the pressure. And then we'll be defining another function. This one is another equation, and again there will be another vector, and that vector will have that vector will have its first index be the temperature. So again, we'll break that vector down, and then we will be returning the equation. So the equation is the due pressure with the vapor mole fraction and the temperature minus the pressure, and then that will be returned in the big function for the due temperature. We'll be returning the root of that equation, and we need to provide an initial guess. And so our initial guess can again just be 298. Shift enter. So now we have all our functions defined. So if we were to find the bubble pressure with 0.3 mole fraction, and let's just say 393 Kelvin, that is the bubble pressure. And if we were to do the bubble temperature at, let's say, 0.3 and 100,000 pascals, that gives us the bubble temperature, but it gives us all this extra information as well. So we really just need the X, and so we can go back and actually just pull out the X. So now it just has the X, and it's actually an array. So if we wanted just the scalar value, we could pull out the first index of that array. And so now it's just the scalar value. And so we can do that for the due temperature as well. And so if we were to do the due temperature, again, 0.7 this time for the liquid, or the vapor mole fraction, we'll do 100,000 pascals. That gives us the due temperature. As you can see, with a liquid mole fraction of 0.3 and a vapor mole fraction of 0.7, the bubble temperature and the due temperature are the same. And so now that we have our functions defined, we can move on to plotting the binary vapor-liquid equilibrium phase diagram. So to plot, what we'll be doing is we will be creating two plots one plot will be the pressure, and so on that plot we will be plotting the bubble pressure and the dew pressure, and that will be on the y-axis, and then on the x-axis will be the mole fractions of the more volatile component, and so that's the component that has the higher boiling point, or the pure, like as a pure compound. And on the second plot, it will be pretty similar, except on the y-axis will be the temperature, not the pressure, and so on that plot we'll be plotting the bubble temperature and the dew temperature. And so to begin, the first thing we want to do is create the values that we'll be putting on the x-axis. So we're just going to call those values Z1, and we're going to create a list of linearly spaced values, and so we're going to be using np.linspace, so that will be linearly spacing the values. And we want it to start at 0 and go to 1, because mole fractions are going to be in between 0 and 1, and we want it to take steps of 0.1, and so that will be 11 different increments. So it's going to just go from 0 to 1 divided by 11, so it'll be 0.1 steps, like increments with 11 steps. And then we need the inverse of that, so we'll call that Z2, so that will just be 1 minus Z1, so like the first one would be 0.1, and the Z2 would then be 0.9. And then we have the set temperature. The set temperature that we are given is 393 kelvins. So we'll put that in there. And so now what we need to do is make a list of values for it. We'll just start with the bubble pressure. And so we need to create a list, so we'll call it bubble P list. And that's going to be the summation of the bubble pressures. So we are just going to create a saturated vapor pressure. We'll just do it so we don't have to type it over and over again. So that's going to be the P dot Pvap at a certain temperature. And so the bubble P list is just going to be the mole fraction times the saturated vapor pressure plus the first value of it, that's going to be the benzene, and then that's going to be adding the second mole fraction times the second index of the saturated vapor pressure, which is going to be the toluene. And so now let's just see what this would look like on a plot. So we're going to fig equals make underscore subplots, and so that makes our plot. And so we need to add to it, so add dot scatter fig dot add underscore scatter. And so we're going to add the x-axis. That's going to be Z1. The y-axis is going to be the bubble pressure list, and the mode will be in line, so it'll be a smooth connected line rather than markers. I'm going to shift enter, and so that's our plot. Again, we're going to be making two plots, so we're going to do a row is the first row and the first column. Yeah. And then, so when we add a second row, or a second column, it'll be plotted right next to it. So let's actually write out what's going to be on the, it's going to be the bubble pressure, or the, excuse me, the dew pressure. And so for the dew pressure, we're actually going to use a for loop. So we're going to use for the vapor mole fraction in the number of points we have on the x-axis. And so for every Z1 value, there's going to be a Y1 value, and so that's just going to create the vapor mole fractions. And then so we also need a vapor mole fractions for the second component, and so the second component mole fractions is just going to be 1 minus the first component vapor mole fractions, which is similar to what we did up here with the Z1 and the Z2. And we are going to put those, the first component and second component mole fractions, in the vapor phase into an array. So we're just going to name that whole array Y. And we're going to do np.array. So that's going to put those values in an array. We're going to put them in brackets. So that's going to be one, the first component vapor mole fraction, and then the second component vapor mole fraction. And now we're going to use our do pressure function to calculate that. But first we need a list to put all of these do pressures into. And so we need to make a do pressure list. And so we're just going to add to that do pressure list. So we're going to use do pressure list dot append, and it's going to append, so it's going to add it using the do pressure function, and that's going to be Y and 2. And we're going to shift enter. And making sure the syntax is correct. And so for our subplot, we're going to add this on. And so we're just going to copy and paste this part here. And instead of the bubble pressure list, though, we will now have the do pressure list. And for our subplots, we need to establish that there is one row and 2 columns. We're going to shift enter. So the error is we forgot to put an S for the syntax. So it's going to scream at us. Alright, so now that's our pressure. And so we need to create the second plot. That's going to be the temperature. And so similar to what we did with the do pressure list, we're going to create a bubble temperature list and a do temperature list. And again, we're going to create a for loop. And so for every Z1 value, so every point on the x-axis, there's going to need to be a mole fraction, so we will call that x1. This is pretty much identical to what we did for the do pressure list. And again, we need to create the second component, and so that's going to be x2, and that's going to just be 1 minus the x1. And then we're going to combine these into an array that's called x. And so we're going to again use np.array, and that's going to be the first component and the second component. And then so now we need to append to the bubble temperature list and the do temperature list. So we're going to use the list name dot append, and we want to append it with the bubble temperature function that we wrote up here. So that's going to need the x and the pressure, and then we're going to need to append the do temperature list. So it's going to add to it, and it's going to add with the do temperature function, and that's going to need the x array and the pressure. And so we need to make sure that we define the pressure, And so the given pressure constant that we have is 150 kilopascals, so we're just going to define that. So pressure is 150 kilopascals. So we would just do 6. Okay. So if we shift enter, that all looks good, there's no errors. So we need to add to the plot. So we're just going to copy and paste this, and so instead of the bubble temperature list, we need the instead of the bubble pressure list, we need the bubble temperature list, and that's going to be in the second column. And then instead of the dew pressure list, we need the dew temperature list. Dew pressure list, we need the dew temperature list, and that's going to also be in the second column. So we're going to shift enter. So the reason there's this error here, and it's a straight line instead of the curve that needs to be, is because the big difference between the temperatures and the pressures is that this needs to be an array because of the root solver. And so it needs to be an array of x1 and x2. And similar for here, it needs to be an array for x1 and x2. And additionally, it's kilopascals, not megapascals, so it needs to be 10 to the third. So the error made is it is xy1 here, and the rest is x just without the y. And so having it without the y made it to not recognize it. And so if we were to remove that y and keep all of the naming constant, we would get the curves that is needed. And so these are our phase diagrams for the binary vapor liquid equilibrium. Now we can clean it up and just label everything and make sure that everything's easy to read. So we can name each of these. So this is the bubble pressure, and this is the dew pressure, bubble temperature, dew temperature, and then we can update the y-axis. So this is pressure for the graph, the plot on the left. So that's the first row, first column. We can copy and paste it. So for the y-axis on the right plot, that is the temperature. And then for the x-axis, the title is now if we shift enter, we have those titles. We can also add a title to the graph, so it is the binary vapor liquid equilibrium phase diagrams. We also want to make sure that the units are labeled. Now if we shift enter, now we have a title. We have the graphs labeled. We can also change the spacing of the x-axis ticks. So if we want to change that, we can use the linspace that we use to actually define the different values on the x-axis. So that's going to go from 0 to 1 with 11 steps. Shift enter, now it goes from 0 to 0.1. And so now we have the plots of the phase diagram all done.